let's look at a few questions on electrode potential, calculations and some essays. Now, look at this question, for example. It says, calculate the standard electrode potential. Calculate the standard electrode potential of the EMF of the following cells at 298 Kelvin. Iron and tin. A cell made up of iron and tin. So, question A, iron Fe Fe2 plus // Sn2 plus /Sn. Aqueous. Now, what we do here is very simple. First of all, you need to identify, this is a cell that is made up of two half cells. That's a cell that's made up of what? Two half cells. So this is the first half cell, which is the oxidation half cell. We always write the oxidation half cell first. And this is the second half cell, which is the reduction half cell. Now, the standard electrode potential of this cell, or the EMF of this cell, is equal to E cell, and it is given by E reduction minus E oxidation, meaning, standard electrode potential of the reduction half cell minus standard electrode potential of the oxidation half cell. Now here, the reduction half cell is tin. So let's go read off the electrode potential for tin. I think I have a table here that will give us our answer. Tin here is minus 0.14. Tin is minus 0.14 here. Let me take iron once and for all if I can. Okay, iron Fe2 plus is minus 0.44. So tin, I'm going to write minus, that's going to give me minus 0.14 minus 0.44. Iron is minus 0.44, and the standard electrode potential of tin is minus 0.14. Both are in volts. Sorry, I missed that. Both are in volts. I don't want to clean because of time. So this will give me minus 0.14. That will give you minus 0.14 volts plus 0.44 volts. And what does that give you? That's plus 0.30 volts. So this is the standard electrode potential of the cell, or we can call it the EMF of the cell. So let's go to question B. In question B, I'll be fast. In question B, it is zinc and silver. In question B, the cell is a cell of zinc and silver. Zinc is the oxidation half cell, Zn2 plus. Then silver is the reduction half cell, Ag plus. Solid aqueous. So let's just take it. The EMF of our cell is going to be the standard electrode potential of the reduction half cell, minus standard electrode potential of the oxidation half cell. So zinc and iron. Let's go take it. I think I know that of zinc. It should be minus 0.76 volts. So let's put that down. So I'm just going to put that of silver here. So it will be that of silver minus that of zinc. So let's go ahead and find the electrode potential for silver. Excuse me, I want to be using this table in this video. Silver is Ag plus. I think I should have it somewhere here if I have not lost it. Okay, Ag plus is down here. Plus, can you see it? Ag plus is plus 0.80. So, and let me confirm that of zinc too. Zinc is Zn, and zinc is what? Minus 0.76. I hope you can see it here. Zinc is what? Minus 0.76. So let's go fix this. So I'm going to write, what did I read? Silver minus plus 0.80. So I'm going to write plus 0.80 volts minus what? minus 0.76 volts, minus 0.76 volts. So I will write that the EMF of my cell is the standard electrode potential of the reduction half cell, which is this, minus the standard electrode potential of the oxidation half cell, which is, you understand, the zinc half cell, which is this. So that gives me my answer. What do I get? Plus 0.80 volts plus 0.76 volts. The EMF of the cell formed by the two half cells will be 1.56 volts, and you must put the sign. The sign is important. E cell, or EMF of the cell, is 1.56 volts. Let's go to question C. In question C, my two half cells are nickel Ni2 plus copper Cu2 plus. So let's go ahead and do that. So my two half cells are oxidation half cell, nickel Ni2 plus aqueous, and what? Copper. This should be two lines, copper Cu2 plus, which is the reduction half cell, and let me not make the lines too long, and Cu solid, which is the, this is the reduction half cell, and this is my oxidation half cell. So let's go ahead and get the EMF of this cell. Now, same way, the EMF of this cell is the standard electrode potential of the reduction half cell minus the standard electrode potential of the oxidation half cell. That's very simple. The reduction half cell here, its standard electrode potential, we used it recently, is plus 0.34. So let's go find the standard electrode potential of nickel. So let's go get the standard electrode potential of nickel on this list. Okay, this is it right here. Nickel is right here. Ni2 plus 2E to give Ni. That's minus 0.25. I hope you can see this. I'm trying to make you see the table. These are standard values you will always be given in an exam. You don't have to know it offhand. So I'll just put it here. Minus 0.25. Be careful not to miss the minus, because this has a minus itself. So when you're subtracting it from this, you understand, this minus should be 2. That's this minus this. You understand? So what does that give us? That gives us plus 0.34 volts plus 0.25 volts. 0.34 plus 0.25. The standard EMF of the cell will be equal to what? Plus 0.59 volts. So with this, I hope you'll be able to get the rest yourself. So as your exercise, let me just give you this as your exercise. So as your exercise, do it from question 1C to, where does it end? As your exercise, do it from question 1C to E. I've done A and B. So answer the questions from C to E. I've done A and B. Now, let's go to something very important. Significance of E cell. Significance of E cell. You will see the significance of E cell is in its sign. When it tells us whether a cell can, a cell is possible in real life or not. You understand? The value of the standard electrode potential of a cell tells us whether the cell is what? Tells us whether the cell is possible or not. And when the cell is possible, it also tells us how much EMF how much EMF is gotten from a cell. It also tells us how much EMF is gotten from what? From a cell. So it gives us two things. It tells us how much EMF is gotten from a cell. So what you need to know here is that when the E cell is positive, when the standard electrode potential of a cell, is positive, then the reaction is what? Spontaneous. Spontaneous means the reaction will easily occur. But when the standard electrode potential of the cell, is negative, it tells us the reaction is non-spontaneous. Let's now continue with the exercise. Let's go to number 2. Let's go to question 2 and start with question 2a. Maybe in that one I will only answer one question. You did the rest yourself. So here it says we should calculate. We are told to calculate. Okay, looks like I've gained it back. Okay, we are told to calculate the standard electrode potential of the EMF of the following cells at 298. So this is a cell made up of what? Iron and what? Made up of iron and silver. This is a cell made up of iron and silver. Okay. I think I'm going to leave that because it shows us another thing. We don't require that for now. So let's just go to B. Okay, in B, the cell is made up of zinc and lead. So in B, zinc is the oxidation half cell, and then aqueous. Lead is the reduction half cell, aqueous. So and solid. So here, this is our oxidation half cell. Let me label this. This is my oxidation half cell. This is my what? Reduction half cell. So the EMF of the cell, is going to be the standard electrode potential of the what? The standard electrode potential of the reduction half cell minus the standard electrode potential of what? Of the oxidation half cell. So that gives us what? Okay, let's go read off the value for the standard electrode potential of lead. Lead is minus 0.13. Can you see it here? Lead is minus 0.13 volt. So I'm going to write that in. Minus 0.13 volt minus 0.76 volt. We have used this value for zinc before. So we go and get minus 0.13 volt plus 0.76 volts. And that gives us what? What does that give us? 3, 6. That gives us plus 0.63 volt. So the EMF of our cell is plus 0.63 volt. This is a spontaneous cell. A cell that can be easily set up. So you do the rest as your exercise. I'm going to be giving you enough to do yourself too now, so that you can exercise your muscles. Answer it from C to F yourself in number 2. Let's go to question 3. I'll be really fast now because of time. Question 3 says, a magnesium rod dipped into a magnesium salt solution was connected through a voltmeter to a tin rod dipped into a tin salt. That means we have two half cells. Magnesium half cell, tin half cell. Are you getting that? It says a salt bridge was connected between them. The standard electrode potential of magnesium and tin are minus what? 2.31 and plus 0.14. Let me jot that down. Magnesium, standard electrode potential of magnesium minus 2.31 volt. Okay, let me jot that down. Standard electrode potential of magnesium minus 2.31 volts. Standard electrode potential of tin is what? Plus 0.13 volts. Let me write that well so it can be clear. Standard electrode potential of tin is plus 0.13 volts. So let's go back to our question. Magnesium and tin. Okay, plus 0.14. Let me correct that. Plus 0.14 volts and minus 2.31 volts. It says write down the cell representation. Determine the EMF of the cell. So our question says we should write down the cell representation. Now, between magnesium and tin, which one is higher up in the series? If you remember your activity series, there is activity series for cations. There's activity series for cations. Let me quickly show you that before we move on. There's activity series for what? For cations. So in the activity series of cations, let's see the positions of magnesium and tin. The activity series goes like this. We use this acronym to remember it. Liposocama. Say it after me. Liposocama R. Liposocama R. Z. Fe. T. Liposocama R. Z. Fe. T. Le. Hyco. Liposocama R. Z. Fe. T. Le. Hyco. Messi what? Messi Plago. That's the acronym, or what's it called? Abbreviations. Those are the abbreviations we use for remembering the activity series so far. Let me read it again. Liposocama RZ fertile Hyco RZ fertile what? Hyco RZ fertile Hyco. This is co here. Then what? Messi Plago. Now take note of something. Each of them is an abbreviation for ions of different elements, and there's a significance around hydrogen. We always say this about the significance of hydrogen here. The significance of hydrogen is such that elements below hydrogen are generally termed not reactive, and those above hydrogen are generally termed elements below hydrogen are generally termed unreactive. Those above hydrogen are generally termed reactive. Metals above hydrogen are generally said to be reactive. Those below hydrogen are unreactive. Then also we say those far up in the series, those very high up in the series, those elements very high up in the series are highly reactive. Then those below them are what? Less reactive. These ones we easily react with cold water. Some of them we easily react with cold water, while these ones in the middle we react with water in form of steam. These ones will react with water in form of steam. Those below hydrogen will not react with water in any form. So we'll get to more of that when we get to inorganic chemistry. So let's now take the names of the abbreviations. I will draw a line downward. Let me change my ink to orange. I'll draw a line downwards like this so that you can see what we mean by all of this. This line shows that as you come downwards, reactivity decreases as you come downwards. Reactivity decreases. So let me write the names of each of them. So this is lithium Li+. This is Po is potassium K+. So is sodium Na+. Ca is calcium Ca2+. Ma is magnesium Mg2+. Al is aluminium Al3+. Zinc is Zn2+. Z is zinc Zn2+. Fe is iron Fe2+. What else? T is tin, T is tin, Sn plus, Sn2 plus, lead is lead, Pb2 plus, Hi is for hydrogen, H plus, Co is for copper, Cu2 plus. I'll try and write that more neatly. Co is for copper, Cu2 plus. Me is for mercury, Hg plus. T, Mesiplago. C is for silver, Ag plus. Pla is for platinum, Pt plus. And Go is for gold, Au plus. So these are the ions in order of their activity. Now, what this means is that if magnesium and tin were to be put together, the essence of this series is to tell you which one is more reactive. Magnesium is up here. As you can see, magnesium is up here. Let's now find tin. I think tin is somewhere below it. Okay, this is tin here. Tin is down in the middle here. So that means magnesium is higher up in the series than tin. Magnesium is here. Magnesium is higher than tin. So magnesium will be the anode and tin will be the what? The cathode. That means that we are going to write our cell like this. The question says we should write a cell representation. Cell representation. So our cell will look like this. The magnesium will be the oxidation half cell, Mg2 plus, giving electrons to the reduction half cell, Sn2 plus, aqueous slash what? Sn2 plus aqueous slash Sn solid. So this is going to be, this stands as our oxidation half cell. This stands as our what? Oxidation half cell. And this stands as our reduction half cell. So we have drawn a representation for the cell. Now, it also says question 2 that we should calculate. Let me check again. It says determine the EMF or the cell potential. They mean the same thing. I think it was just a mistake in number 1 they were writing off twice. So they mean the same thing. Let's go ahead and do that. How do you get the EMF of the cell? The EMF of the cell is the standard electrode potential of the reduction half cell minus the standard electrode potential of the what? Oxidation half cell. So what we are going to do is very simple. The reduction half cell is the tin half cell. The reduction half cell is the tin half cell. The oxidation half cell is the magnesium half cell. So let's go get the standard electrode potential of tin. This is it here. Tin is in the middle here, plus 0.15 volts. So I'm going to write plus 0.15 volts minus, let's go get the standard electrode potential of the magnesium half cell. That's minus 2.31. Okay, I don't even need to come to the table. We've been given in the question. Sorry, I forgot to use that. That the standard electrode potential of tin is plus 0.14 volt, and that of magnesium is minus 2.31 volts. So we just keep to what we have been given. We've been given in the question up here. I think it was up here. So we have it already in our question. So we just use what we have, because you will not have tables in all exams. So you use what you are given in the question. This gives us plus 0.14 volt minus what? Plus minus times minus is plus 2.31 volt, and that's equal to plus that's equal to what? Plus 2.45 volts. So the EMF of our cell is plus 2.45 volt. That answers question 3. Let me pause here. You do your classwork and send me your solution and your work. So we'll continue in the next video.